Hey guys, welcome to another video. So today we're going to start a new topic in the Year 12 Advanced syllabus. It falls on it used to fall on the series and sequences topic, but let's just call it financial maths. So financial maths. So the financial maths topic, started back in Year 7 when you started learning about money. In Year 9, you did a bit of compound interest. But in Year 11 and 12, it goes to another level when it's incorporating the topic of series. So I'm going to divide this topic into 3 parts, which covers the sort of 3 common types of questions which are bucketed that you see in past papers. It's interesting for those that are curious about the old syllabus versus the new syllabus. In the old syllabus, there was only 2 buckets. There was superannuation and savings, which is what we're going to do right now, today. Then there's home loans, right? They're the 2 topics that were covered in the old syllabus, but in the new syllabus, they started throwing around this word called annuities. Yep. So with annuities, I mean, I'm an actuary by trade. Actuaries love the concept of annuities. It's their bread and butter. So unfortunately, in the new syllabus, the way they've dealt with annuities, they basically just really diluted it and watered it down to using tables to help you do your thing. So, but I will touch on it in the 3rd lesson. So today, let's start with superannuation. So I've rearranged my camera structure, so I'll be looking this way. So, I won't be looking directly into the camera, so it's slightly different. So, also, before I begin, if you haven't already done so, please subscribe to the channel, like the video. It just helps with the YouTube algorithm. So, guys, let's start. So I'm just going to zoom in here. So the first bucket of questions, superannuation, is a classic, right? Where you basically save up, or savings, right? Where you save up an amount of money each period, each year, each quarter, each month, and it builds up to retirement or superannuation. But these questions can also look in the context, be seen in the context of someone saving up money and then withdrawing it at a certain date. So now, let me give you a really easy question to begin with, and then we will do a few past paper questions. So here we go. So the first one, example, let's say Fred plans to retire at the end of 20 years and decides, handwriting the best today, but decides to set aside $12,000 at the beginning of each year. In a superannuation fund. Earning. So it is a really long 1 sentence, but I've mastered the art of asking this almost in like 2 sentences. Earning 8% better per annum. Right. And the question, so per sentence, all the detail you need. How much will he have in the fund when he retires? Look, that is the classic structure for a superannuation savings question. Now, what I'm going to do something quite different. I'm going to actually show you diagrammatically what this question is all about. When you look at textbooks, a lot of textbooks, if any textbooks for that matter, a lot of textbooks don't show you a diagram. They just basically show you the maths behind it. And I find that's fine, but it's always good to sort of picture what the math is all about. So I'm a big fan of drawing this diagram for my class. So feel free to use it in an exam. I think it's quite useful. So here's a number line. So in this case, let's highlight the key aspects of the information, right? So you got 20 years, retires at the end of 20 years, sets aside $12,000 at the beginning of each year. Maybe I should highlight that beginning of each year, and the fund pays 8% per annum. Perfect. So in the number line, we have, let's say this is time 0, this is time 1, time 2, and then at the end of the period, 20, 19, 18, and some stuff in between, right? So the way we're going to do it is, I always like to say to my students, do 3 years on the left, 3 years on the right, at the end, just so you can actually get the picture right. So in this case, Fred puts in, now, the notion of putting in at the beginning of the year is key, because sometimes if I was to get fancy with a question, I'd say he sets aside $12,000 in the middle of the period or middle of the month, etc., middle of the year, just to see how students can react to it without, just relying solely on the formula. So some students do this purely by formula, and they can't be flexible when the question changes. So for you right now, the diagram is actually quite flexible. It is. So it sets aside $12,000. So I'm going to say, this is almost at the beginning, year 1, this is year 2, and obviously this is year 20, year 19. So at the beginning of year 1, at this point, he puts in 12,000, right? And the way I'm going to depict it for you is that this $12,000 stays in the fund and gets compound interest for 20 years, right? So that $12,000 at the end of, when he retires, it becomes 12,000 times 1 plus R. So in this case, 1 plus R is 1 plus 8% to the power of 20, right? That's just year 9 compound interest, year 8 compound interest at the point of, and just be clear, this point he retires, right? Now, what we're going to do is then say, okay, that's the first payment of $12,000 he makes at the beginning of year 1. So that's this year done. At the beginning of year 2, right, at that time period of 1, he puts in another $12,000. And that one also gets compound interest. Now, the key difference is that it gets 1 year less compounding, right? So instead of 20 years of compounding, this payment gets 1.08 to the power of 19. You can see the pattern then develops, right? Blah, 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 blah. Now, let's go and explore year 19. So at the beginning of year 19, so at this 18 point, he puts in $12,000, and that gets 2 years of compounding, right? And similarly, at the end of the last year, at the beginning of that last year, 19, he puts in his last $12,000. And because he put it in at the beginning of the year, he'll get 1 year of compound interest, right? So you can sort of see the stream of payments that I need to add in order to get the final payment, right? So what I'm going to do, maybe I'll use a red pen here. So if I add that, and I add that, dot, 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 there's all these ones in between here that we have to capture as well, right? So dot, 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 plus, plus. This represents the series of payments that I need to add up to get my total number, right? So in a textbook, a lot of the times they would just have this series done in a string, right? But they don't tell you really, or it's better to sort of see why it developed in this way. So when I add these up, I always say to my students, put the smallest power first. So I'm just going to say, let's go total equals to, scroll over a bit. Total equals to, put the smallest one first. So 1.08 to the power of 1 plus 12. Your teachers will love seeing you do this line of working out where you, before you do the final answer. So then dot, dot, dot represents guys in between, and 12,000, 1.08, power 19, and the last payment there as well. Let me see if I can fit it in. I couldn't, so I'm going to preview that PowerPoint. Shift it over. 1.08 to the power of 20. Beautiful. Right, now, to clean it up and to really develop our GP or our geometric progression, I'm going to factorize 12,000, and I can see there's 1.08 in all the brackets at least. Yeah. Now, when I take out 12,000 and 1.08 from the first term, I'm left with 1. When I take it from the second term, I'm left with only one of these 1.08. So basically, you can sort of see if I take 12,000 1.08 from every term, the power of the 1.08 just drops, and that's the only thing that's left over, the 1.08, 18, 1.08, 19, right? And there lies my geometric progression, right? It's a geometric progression because it's got a common ratio, a common multiple that increases by 1.08, where just to be clear here, my first term, my A is 1. My ratio is 1.08. And I always say this to my students, just be very clear, right? It looks like there's power in 19. It looks like there's 19 terms. There's actually 20 because the number 1 has no power, right? No 1.08. So whatever that power is, add another one there. The n terms is 20, right, for my formula. And what was my formula again? The sum of the GP is equal to A R n minus 1, right, over R minus 1. Now, some teachers teach you the formula where the 1 comes first when the ratio is less. It doesn't matter. Use one of them, they both give you the same answer. Guys, plug that in, and you get 12,000 1.08. I'm just gonna use red to denote the GP substitution where it's A, which is 1, is replacing this guy, right? Times 1.R to the power of n minus 1, R minus 1. And if you punch that all into your calculator, the total amount that Fred gets when he retires is 593,075. Let's always do it to the nearest cent. Yeah, not too bad. That's how you would do it diagrammatically. Yeah. So what I'm going to strive, I won't do too many questions today, but I'll strive to draw the diagrams wherever we need it, right? That's how I teach superannuation, right? Through a diagram. Sometimes it feels a bit longer. Now, sooner or later, you can drop the diagram, right? But just for illustration in this lesson, let's do it now. Let's do a number of questions where we explore past paper questions. So the first one I'm going to do comes from bottom. So you can see, you know, like each time you see one of these financial maths questions in a past paper context, you know, it's like 5, 7, sometimes 9 marks, right? So if you can't do this in an advanced paper, it's not looking good, right? So make sure you can do these. And sometimes there are a lot of words, right? And that's why it makes it hard. So in Balcombe Hills, 2015, Karen contributes to Superfund. Superfund contributes $250 at the start of every quarter. Quarter is a key word there, right? So let me highlight that for you because it determines the number of periods that we have, right? Interest rate 8%, just like my question before, compounding quarterly, great, and continues to make 30 years, right? So interest. Now we need to convert this interest rate into a quarterly rate. So that's like 0.8 divided by 4, which is 2%, so 0.02. All right, 30 years, we need to convert that to quarters. So n is 30 times 4 is 120, right? So let's just line all our ducks in a row. So, okay, here we go. The question is, how much does she contribute altogether? Now, that's suggesting just no compounding. How much, if she put $250 every quarter, how many lots of 250 did she actually put in, right? That's what part 1 is all about. Number 2, what is the value of her initial 250 at the end of 30 years? So she put in $250 at the start, right? Just for that first payment, what's that value after 30 years? So that's just simple compound interest, $250 for 30 years at 2%, right? And then the value of the, that's really the series question for through. You can tell by the mark allocation, that's 3 marks. So guys, part 1, very simple. We're talking how much does she contribute altogether? It's literally multiplying 250 by the number of times she pays, which is 120. Yeah, do that. I mean, that is 30,000, right, on your calculator. or should be. Maybe I should have a calculator in hand. I don't. It's fine. Anyway. All right, next one, $250. You know what? Before I do the next one, I'm going to draw a combined diagram just because I want to, right? Just to show you for 2 and 3. So 2 and 3 basically, you know, if I was to draw this diagram, just really to explain it, right? We're talking 0, 1, 1 and 2, and just be careful here, not 30 years, right? We're talking quarters. So 120 quarters, 119, 118, right? So just to be clear there, that is quarter 1, that is quarter 2, this is quarter 119, this is quarter 1. Right? So Karen makes 250 here, and that gets 120 quarters of compound interest, 1.02, right? Comparable 120. And then she makes another 250 here, and because that's a quarter later, you get that power of 119. Dot. Again, so we got this done, right, 2 quarters, now quarter, 119. If I put 120 there, it gets 1, 2 quarters of compounding. So not 120, 250. By the way, in the comments, I tend to make some mistakes in every sort of lesson that I do. Feel free to let me know, right? And then I will make a comment to update it. So let me know if I do some arithmetic error, but hopefully the concept is fine. So the last period there, so that's done. The last period, so as well, 1 quarter of compounding. And that's our accumulated value for part 3. Now, what's part 2 then? Part 2 is basically saying, what is the value of the initial? That's this guy. So all they want for part 2 is this amount, right? The compound amount of the initial $250. So really, for the first one, it's 250 times 2% to the power of 120 quarters, right? So that should give you, if you punch it in the calculator, I think it's 2691.29. Right, that was part A. Oh, sorry, part 1. That was part 2. Quite simple. And then part 3 is basically this thing here. Right? This is part 3. Right? Yeah, the sum of all payments. So it's going to write total value equals 2. So remember, when you do this, it's best to express it in lowest power first. So you go 250, 1.01 to the power 1, 250, 1.02 rather, to the power 2 plus 250, 1.02 to the power 119, 250, to the power 120. And then seriously, if you've done this, 10, 15 times in past paper question context, you get a bit robotic, right? You basically go, okay, I see all that. I'm going to factorize out 250, 1.02, right? Because that is in all of them. Square bracket there, taking it all out, that's 1 plus 1 of these plus. If you take one out, that's 118. Take one of those out, 102, 119. Here we have a GP, right? Where we know that A is 1, R is 1.02, and N, because it's 119 with a 1 at the start, there's 120 terms. N is a number of terms, right? So then when I punch this, or sub this rather, into my GP, sum of the GP formula would be A times R to the power of N minus 1 over R minus 1. Yep. If you punch that into the calculator, round it off to the nearest cent, 124, 505, 83. Yeah. Pretty straightforward. So how's that? So I really want you to visualize it via the diagram. Now, in a test, you need to do, not really. If it works, if you understand it, perfect. But that's how I show my students how to visualize the payments, right? And this is really cool, especially for questions where, they try to get fancy. And somewhere in the middle here, they might change the rate. And what that means is that you basically change the rate here, et cetera, et cetera. That's how you do it. Let's do another. Let me see. I want to do one. Yep. So I want to do one where they try to make it harder by giving you dates, right, or birthdays and stuff like that, just to really get your mind working. So this is from Hornsby Girls, right? And as you can see, once again, 7 marks, right? 7 marks in a 2-unit paper, advanced paper. That's quite heavy. Also, you can see that there's a lot of words, right? So just be conscious of that fact. Let's see how we go. Yeah, that's how we go. Hornsby Girls, 2008. Every year, starting on Lana's first birthday. We're starting on her first birthday, right? The grandparents deposit $100 in a special account, 9% per annum compound annual. We're talking years. First birthday. On her 21st birthday, instead of depositing $100, they deposit a lump sum. Lump sum just means one-off payment of $10,000. After this, they stop. Okay. So let's have a quick look at the questions, and then I'll draw a diagram, right? How much did Lana have an account after the lump sum was deposited? So how much did she? That's the total value, including. So what happens is, on her birthday, on the last day, they deposit, instead of putting in 100, they put in $10,000. Right? That's now. If I was to draw a line here, normally that is a superannuation question done, right? But there's more, right? They want you to, a lot of cool questions basically have a bit more to it, right? And the best ones that I've seen combine superannuation with next lesson's concept of loan payments, right? It's neat. There's a HSC question that does that as well. Okay, let's see what else we're doing. Lana left all her money until her in the account until her 26th birthday, right? What was the balance? Good question, right? So she basically, whatever you calculate number 1, she left it for another 5 years, right? And then what was the amount? And part 3, what is single amount of money would her grandparents needed to put in her first birthday so that they had the same as their 26th, right? Single amount of money. So basically, you're going to calculate a number for number 1, and then you're going to leave it till 26th birthday. And then we need to calculate what's one lump sum money that they could have done at the start of the year that would have given the same amount. So I love this. Right? It's all connected. So once again, let's focus on part 1. When we focus on part 1, we basically need to develop this diagram again, right? Now, but this diagram is a little bit different. So basically, let's see what happens, right? What are we saying? So the first payment occurs on her first birthday. So when Lana is 1, and when Lana is 2, actually, I'm going to do something different. I'm still going to use 0, 1, 2, blah, blah, but in green, this is her age, right? She's 1 here, 2 here, 3 here. Now, how old did they stop at? 21. So 2019, right? And so you can see that the difference is always 1. So this is 18, 19, 20. That's important because the black is my compounding years, right? But the green is my, so they could have started this question at age 15, right? So then always identify the compounding years because that's actually the mass, but the age determines when you start and stop, right? Quite important. So let's see. What happens here? So at age 1, they put in $100. And that $100, remember, the black is the compound. We're not compounding for 21 years, over 20 years, right? That black gets 20 years of compounding. What's the interest rate? 0.9 to the power of 20. Is that okay? 20 years of compounding, she's 21 years old, right? Now, and then the same goes every year, right? They put in another $100. 19, right? Now, this is cool, right? So in the 18th year, right? Or 19, when she's 19, they put in $100. That gets 2 years of compounding, right? Just like we did before. 2 years. When she, in the last year, right? When she's 20 years old, they put in the last $100 amount. Now, and what is different, right, between this question and the ones before is that they make another payment. They make another payment. When Lana turns 21, they put in $10,000. When she's 21, they put in $10,000. Now, when they put it in at the end of the period, there's no interest. So this just becomes 10,000, right? We don't compound that at all. It's just that at the end of the period, they put in another $10,000 and then stop, right? So what that means is we're going to do this in two parts, aren't we? We're going to have a GP that captures all the $100, right? And then we're going to have adding to it a $10,000 amount at the end, right? So to do this question, we basically go total equals. So we're going to do the green first, right? We're going to do the green where it's maybe I will use it green just to really hammer home the color reference. 1.09 para 1, 09 para 2, here it is, and plus 100.09 para 19 plus 100.09 para 20. And then, guys, we or they put in another $10,000 on the back of that. This question is neat because there's a GP element, and a lot of students don't know how to react to the 10,000. They don't know whether to compound or not. But it's made at the end, right? At the end, because the moment they pay that 10,000, they stop, right? It says it, right? The last sentence in the paragraph, right? So we apply the GP mechanism to this, where we go, that is 100, factorize 109 there, factorize 1 plus 0.09, para 1, 1.09 para M18, 1.09 para 19, right? And then plus 10,000 on the back of that. Just like before, guys, we're gonna treat this as a sum of the GP, where identify that the A value is 1, R is 1.09, and N 19 at the back, with the ones, that's 20 payments. And so then my calculation is going to be that 1.09, just break just like I did before, 1 times 1.09 is para 20 minus 1, 0.09 minus 1, and don't forget the 10,000 on the back, right? And if you did do that all on your calculator, you should get 15,576. And just to be clear, for those that just did the GP with that 10 grand, you get 5,000 something, but with the 10 grand in there, you get 15.4. That's 3 marks. So how's that? So that's aside from 10 grand, the green part at least is very textbook. Yeah? All right, now I'll do questions 2 and 3 over here because they're quite straightforward. Oh, sorry, the working out is very quick, but the concept is, can be confusing. So this question now, save whatever you calculated in part 1 in memory, because it says she left all her left that money in the same bank account without adding to it for 5 years. So this is just compound interest. We're going to compound that amount there in the blue box downstairs, 5 years at 9% per annum. Yeah. So basically, the amount is, now I'll use the rounded off figure. You should use the one that's unrounded. That times 1.09 for para 5. Yes, because you're just compounding, right? So then you get that to be 23,966. Right. So once again, save that in memory because you're going to need it for part 3. So quite simply, if I left it for 5 years, that's what it will become. Now, part 3 says, what is a single amount, right? So it's like saying if I drew the diagram, right? 0, 26 years, right? Forget about it in between. What is the single amount that, let's go, what is the X? I put in X, right? And that X gets compounded by 26 years of compounding, right? 26 on the 26th birthday. 26, so that's 25 years of compounding, right? Just be clear there, right? In terms of age, remember age 1, age 26, that's 25 years of compounding. Right? So basically X, maybe it's in the X, use X because it also times, right? X times that equals to the 23,966.30. Let me say that again. We're going to put in one amount at the start for 25 years, compounded at 9% for 25 years, and that should equal to the amount that she has right now at the end of 26 years, on her 26th birthday. Right, so you basically equate that, and then to make X the subject, then you basically just divide that bracket over. So 23,966.30 divided by 1.09 to 25. And if you punch it in the calculator correctly, you should get 2,779. Yeah. So once again, the diagram there, feel free to use it in an exam. Probably don't need to, but it's an illustration of what, it's a good visualization tool for you to use, right? Whenever you do questions like this. Look, guys, that hopefully gives you a flavor of how we attack this. I want to, maybe I will do this topic in 4 parts, where this is lesson number 1, superannuation savings, number 2, loans, number 3, annuities, and then I will come back and do a sort of harder past paper lesson, right? Just to really show you where this topic can go. Thanks for that. Once again, if you haven't subscribed, please do so. Send me a like, tell your friends. I'll see you guys later.